Hello again, and we're going to do one more example of work, finding normal times and standard times. So this is establishing standards, as I did in the last lecture that I posted, establishing standards for benchmarks that people need to meet. So we're going to do two things. We're going to determine sample size, those calculations, I showed you that in the slides, and then we're going to calculate some standard and normal times to show how you would do that. So the first thing is sample size for work sampling. And there are two things that we could do for that. The first is figuring out the allowance factor. And if you remember, the allowance factor was the amount of time that you adjust time for stuff that isn't critical to the task. So it is breaks, it is replenishing. I think I used the example in the lecture of a housekeeper. So they're not only making up rooms, but they're replenishing their carts, they're taking breaks, they're going up and down between rooms and those sorts of things. So the allowance factor is the proportion of their total time that they spend doing stuff that isn't that specific task. And you use that allowance factor to adjust the time so that you can set an expectation of how much they can get done in a day. So this is the sample size for figuring out the allowance factor, and the formula is n times z squared p1 minus p, and p, as was the case with the p chart, is the proportion or the size of the allowance factor over h squared, where h is the acceptable level of error, and this is usually a small number. P is the proportion allowance factor that you expect, right? So what you're doing here is coming up with a measurement of the actual allowance factor, but you have to have sort of a guess or an estimate of what that might be. And Z is the standard normal deviate. And if you look at the desired confidence interval, which you would be given, 90%, 95, 95.45, 99, and 99.73. Just making sure I'm still on camera. Yep. And then the Z to use would be 1.65, 1.96, 2, 2.58, and 3. These you could easily look up in the standard normal table. That's where I got those numbers from. So if that's the approach, let's do an example. So the question becomes, how many times should you sample to determine the allowance factor you want 95% confidence interval with only 5% error, you believe the starting allowance factor is 20%. So then you just plug it into the formula. N is equal to Z squared P 1 minus P over H squared. So N in this case is equal to 1.96 squared, 0.2 times 1 minus 0.2 over 0.05 squared. Which should give you, if I've done my calculations correct, 614.65. Always round up is 615. So you would need to go 615 times and see whether they're actually doing the work or doing something that's in the allowance factor to see if your estimate of the allowance factor was correct. So that's relatively straightforward. If, on the other hand, you were sampling for how long it was, so if you're sampling for time, which is how long it takes, then the formula is N is equal to Z times S over H x bar squared, and in this case S is expected standard deviation. In this case I would give it to you, but in the real case you might do some sampling, come up with a sample standard deviation, and then use it to do a statistically significant sample. X bar is the expected average time. And so the bigger S is, the bigger your sample is. So the more variable time is, the bigger your sample is. So in this case you have a desired accuracy of 5%. That's pretty normal. Confidence is 95%. These are just the parameters of the question. So I would ask, you want to sample for time, you want to have 5% accuracy, 5% error, confidence is 95%, the sample standard deviation is 1, and sample mean is 3. So you get the question. You're trying to determine how long a certain activity takes. You've done a small sample, you have an average of 3 and a standard deviation of 1. You want a confidence interval of 95% with an error rate of 5%. You would then plug it in. N is equal to 1.96, which is Z times 1 over 0.05 times 3 squared is equal to 170.74 equals to 171. So 171, you would have to record how long it takes 171 times to get an accurate measure of the accurate or of the average time. So again, relatively straightforward. You'd be given the formulas and you would just be expected to know how to plug stuff in. So now I'm going to do a problem. So you've sampled now and you're evaluating, you now want to establish normal times and standard times for which you can benchmark. I'm going to show you a question here. I'm going to scan it. This is from quite a few years ago when I taught this in a different program. And the question, I'm expecting you're going to have trouble seeing those. So let me see if I can zoom in on that a little bit. So, you are the new operations manager for the No-Tell Motel. Your first observation is that you usually have too many housekeepers scheduled. You regularly send staff home, but your employment contract means that if staff comes in, you have to pay them for at least 4 hours. Your housekeeping manager says he doesn't know how many people to schedule because he doesn't know how long it takes to clean a room. So, A, your first job is to develop an allowance factor for calculating standard time. You know that you need to make a number of observations to get statistically significant and accurate allowance factor. If you want to be accurate to within 5%, 99% of the time, and you currently expect that staff are spending 30% of their time doing non-cleaning activities, how many observations should you make? What do you think would happen to that number if it changed to 97% of the time? You don't need to calculate the number if you don't want. Tell me what would happen to it. So, let's do A first. I'm going to zoom back out again. So, part A is sample size. We're doing it for allowance factor. So, Z squared P 1 minus P over E squared. E is equal to 0.05 as we saw in the question. At 99%. Z is equal to 2.68. Sometimes people use 3, but we will use accurate number. And P is equal to 0.30. So sample size equals 2.68 squared times 0.3 times 1 minus 0.3 over 0.05 squared is equal to, and I'm going to calculate it because my example used 3, so I'm going to grab my calculator. .68 squared times 0.0 times 0.03 times it's not 0.03, I was right the first time, times 0.3 times 0.7 equals divided by 0.05 x squared equals 603.32 equals 604. So you would need to sample 604 times to get a statistically significant 99% accuracy, within 5%, 99% of the time. And away you go. If you use 3, you would do $756, and I did that to highlight that if the number changed to 97%, Z would go down, so the sample size would go down. So if your confidence interval goes down, then the sample size you need would go down. So that's the answer to the second part of that question. So we've answered answered part A. I could ask you to calculate it. I could ask you a multiple choice question, up, down, we can't tell kind of thing for the second part of the question. So now if we go back to that question, and I'm going to zoom in again. Part B is, just check my notes here. If you should wait until you have made sufficient observations, but you want to calculate a standard time to use until you have done all those observations. You get 2 samples from each of 2 staff. The data are provided below. Using the estimated allowance factor, which was 0.3, calculate normal times and standard times for room cleaning. So let's do that. I'll write out the data again so that you can see it, and we'll keep working through. So the first thing you need to do is get averages for both staff to get normal times. So there were 3 things. There was bathroom, bed, and then tidy and vacuum. So staff 1 had 17 minutes for the bathroom and 19 minutes for the bathroom, divided by 2 to get the average. And then we're going to multiply it by the allowance factor. And the allowance factor, by the rating, not the allowance factor, by the rating. And so this staff member had a rating of 110, so that means they were 10% better than average at cleaning the bathroom. So if you used their actual average and didn't acknowledge that they were better than average, you would set an unreasonable expectation. So we multiply it by 1.1 and we get normal times. So normal times are average times adjusted by performance. So you would get 19.8 there. So it's just essentially the average here, which is 18, times 1.1, which is a 10% improvement, which would give you 19.8. So we do the same thing for bedroom. We get 9 plus 11 divided by 2 times 1.07. So you've got a rating on these people, and here we've given the rating. You could calculate the rating of an individual based on normal times that you've established overall, and then see how they do on average relative. It allows you to say, well, you're rating better, perhaps we'll give you bonuses, or you're rating worse, you need to improve. Equals 10.7, and then general tidying was at 13 plus 11.75 divided by 2 times 0.95. So in this case, this staff member is better at the bathroom than average, is better at the bed than average, but is slightly lower than average at the vacuuming and tidying, equals 11.8. So the total room is 42.3 for staff 1. We would do the same thing for staff 2. Bath, 21 plus 22.5 divided by 2 times 1. So this person's rating was 100, which meant that they're exactly average for this, equals 21.8. Bed was 7.5 plus 8.5 divided by 2 times 1.15. They're better at the bed than average,